For our final project, simulation, we modeled 4th floor Grainger. The group members here are Alex Moxon, Jessica Macklin, Roman Ordonez, and Eric Sandoval.
Let us begin our journey.
One of the things I found kind of annoying at 4th floor Grainger is that lack of space. Sometimes it gets very loud, and then especially for group projects.
6-person seating tables are worse because less people go there and there's always a seat left in the middle. So if they had more of the 4-person ones, then it would be more effective.
When you come here to study even by yourself, it's hard to find space.
I come to Grainger mostly at night, and at about 9 o'clock, it's pretty packed.
It can be kind of frustrating because sometimes, like on Sunday night especially, you come here and there's not many seats.
Finding a table or a place to study on the 4th floor is actually really hard for me between the hours of 4 and 10, just because I have to move around a lot, I have to find open space. Sometimes it's like hard to study with their seats so cramped up, and sometimes I like pull up a chair.
So today it was okay finding the spot because I only had one person with me, but if I had a group of like 3 or 4 people, like I would not have been able to study here.
Do you find yourself leaving?
Sometimes, yeah, especially Sunday nights.
After conducting interviews about student experiences on the 4th floor of Grainger Library, it is evident that students have difficulty finding space to study in groups. We decided to do something about this by creating a simulation of the 4th floor and trying to find an optimal seating arrangement to reduce balking. Our simulation focused specifically on the group study areas of the 4th floor between the hours of 4 and 10 p.m., which was selected since this is when the 4th floor is most crowded. In order to create the simulation, key assumptions were made. First, students only enter the 4th floor from the elevator. Second, there is 1 elevator arrival per minute, carrying a random number of individuals, each assigned to a random group size. Students are then put in a waiting area until their full groups arrive, at which point they search for a table. This simplifying assumption was made because students often wait for their groups before finding a table, and they only choose a table that will fit the whole group. The final assumptions were that tables of 4 are full if there are already 3 or 4 people at the table, tables of 6 are full if there are 4, 5, or 6 people, and students do not pull up chairs from other tables. Before creating the simulation, initial data was collected. This included the current number of tables and table sizes, the number of students to arrive from the elevator every minute, what area of the floor they study on, the size of groups each individual studies in, and how long they stay at the library. We found that the current setup of the library has 32 4-person tables and 8 6-person tables, and the students were surveyed to determine where they typically study on the 4th floor, group sizes, and how long they stay. Number of people to arrive every minute was determined by sitting for 6-hour periods from 4 to 10 p.m. and counting the number of individuals to exit the elevator each minute.
Displayed is the entity attribute hierarchy for our model. At the top, we have the system being modeled, Grainger 4th floor. Within the 4th floor is the elevator, which delivers individuals to the floor at the rate of 1 arrival per minute. The elevator contains 0 to 8 individuals based on different probabilities calculated during data collection. Within our sigma model, this is depicted by the variable NP, or number of people. Individuals in the system possess a unique group size. This is used to determine what size group they will be a part of. The entries of array GA are incremented accordingly. For example, if an individual enters the system and is assigned a group size of 2, this is unique to this individual, and GA of 2 will be incremented by 1. Upon arrival, individuals will be assigned this unique attribute based on data from the SurveyMonkey. Groups are composed of individuals who possess the same unique group size. A group receives a unique index A in order to be tracked throughout the system. Groups are also assigned a group size defined by GS of A group table GT of A, and a group service completion time of GSC of A. GSC of A will take values distributed normal with mean 3.6 hours and standard deviation 1.14 hours. Due to the fact that the simulation model is in minutes, this value will be scaled 60 times. Tables hold groups who have been seated in the system. Each table possesses a unique index 0 through 39, as there are 40 tables present in the system. Based on our assumptions, these tables will have maximum capacities. More specifically, the tables will have a table status defined by the array TS, which will take a value of 1 when full and 0 when available. Tables also have table populations defined by the array TP to keep track of how many individuals are at the table. The model was verified by running the simulation and observing the output of individuals who enter the system. Initially, under the assumption that individuals exiting the elevator were already with their respective group, the simulation was outputting around 1,200 students entering the system within the 6-hour study period. However, during data collection, only 700 to 770 students were entering the system during the study period. Therefore, the initial assumption was discarded. The final assumption is that students will wait for their party in an imaginary buffer area before searching for a table. The final model produces around 680 to 770 students in a 6-hour study period depending on the seed, which is much more realistic. Displayed is the event graph built in Sigma for our model. 39 versions of this model were made in order to mimic hypothetical floor plans. Init, or initialization, is used to initialize all necessary variables to 0. ITab, or table initialization, is used to initialize the floor plan of the system. The initial conditions at 4 p.m. of the current floor plan were observed over a span of 5 days and averaged. ITab will initialize the 40 tables with the displayed initial conditions. These are unique to the floor plan of the model. Partially filled tables are randomly populated with 0 to 2 for 4-person tables and 0 to 3 for 6-person tables, and all occur with equal probabilities. ISC, or initial service completion, is scheduled by ITab with a delay of GSC of A, or the service completion time of a group initially in the system. During the execution of an ISC event, table population and status will be updated based on the group A that has completed service. Arrival, scheduled once ITab has finished initializing all tables, is analogous to the elevator in our system. With probabilities computed during data collection, an arrival event will bring a batch of students ranging from 0 to 8. This number will be assigned to NP. Arrival events will schedule arrival events with a delay of 1. GA, or group assignment, is scheduled by an arrival event when NP is greater than 0. Within GA, for each iteration, an individual will be assigned a unique group size, and the array GA will be incremented accordingly. NP will be decremented per iteration, and GA will self-schedule while NP is greater than 0, as some individuals are still waiting to receive a unique group size. With priority 1, to avoid false scheduling, an enter event will be scheduled once enough individuals possessing the same unique group size are present to form a group. This is done by use of the mod function. Within an enter event, the group size will be decremented from the corresponding entry in the array GA. This also utilizes the mod function. Total groups to enter the system is tracked in this node. ToComp is a holder node for individuals or groups of size 1 who are on the floor but not seeking table study. This event is scheduled by enter when GS of A is 1 and by utilization of a uniform random variable when the individual is determined to be not seeking table study. Search for is scheduled by enter when GS of A is less than 5 and the group is present for table study. This event searches through the number of 4-person tables present in the given model's floor plan and checks to see if a table is available, and if so, whether or not GS of A can fit within this availability. Search for will self-schedule while 4-person tables remain to be searched through. Search 6 will be scheduled by enter when GS of A is greater than 4 or by search for when a group fails to find a table. Search 6 will iterate through tables of 6 present in the model in a similar fashion to search for. If a group still cannot find a table, the group balks in this node. SC, or service completion, is scheduled by either search 6 or search for when a group becomes seated. It is scheduled with delay GSC of A, and during execution, table population and table status will be updated accordingly.
For the data analysis portion of the project, we first narrowed down our search space by running a few seeds on all of the models. We found that balking was lowest when there were between 4 and 7 4-person tables. We then ran 1,000 seeds on those 4 models as well as the original seating arrangement model. After running the models, sample mean and sample variance of balking rate were computed. These values were then used to determine a 95% confidence interval for balking rate. Because sample variance is being used as an estimator for variance and actual variance is unknown, the t-distribution was used to construct the confidence intervals. The results from the models show that average balking rate is lowest when there are 4 tables of 4. With this arrangement, with 95% certainty, balking rate falls between 26.24% and 26.25%, compared to the current setup with balking rate between 30.64% and 30.65%. Because of the minimized balking rate, we are declaring 4 four-person tables to be the optimal seating arrangement for the 4th floor of Grainger Library.
Thanks for watching. See you next time.